The foundation of modern civilization is electricity. We run our appliances, our computers, our entire lives off of this vital resource. But how does it even get to your house or apartment? Bulbs, solar panels, and generators allow individual homes to generate their own power. For most people around the world, they rely on electricity being brought to them through power lines from power plants, either renewable or fossil fuel. Transmitting electricity for one house can be done through just a small wire. But when you have to transmit electricity for an entire city, it requires incredibly thick and large high-powered transmission lines. These massive lines run at high voltage, upwards of 500 kilovolt with thousands of amps, often hundreds of feet up in the sky to keep them away from people. High voltage towers are essential. Earlier, DC systems developed by the Edison's company could not transmit the power more than a couple of kilometers. Thus, only the customers within that much short range of the DC power plants could get the power supply. As the transmission distance increases, voltage drops significantly due to the I-square-R loss. A solution for this is to increase the transmission line voltage, but there was no convenient way to change the voltage level of DC power. With the development of AC, it became very easy to change the voltage levels of AC power using transformers. Power could now be transferred over long distances using AC by stepping up the voltage level for transmission and stepping down again for utilization. A vast majority of transmission systems today use three-phase high-voltage AC power, but the development in power electronics made us reconsider the DC power for transmission purposes. A major problem that Edison could not solve was to increase the transmission voltage of DC for transmitting the power over long distances. With the development of mercury arc valves, it became easier to convert the power between AC and DC. The AC power could now be converted into DC after stepping up the voltage using a transformer, and at the end of the transmission line, it could be converted back into AC for stepping down. This made high voltage DC transmission technically feasible. Using this technology, the world's first HVDC transmission link was built by ABB in the late 1950s. However, the converter equipment was very large and expensive and required a lot of maintenance. Soon after, solid-state thyristor valves were developed. They were smaller and cost-effective. Improvements in electronics are responsible for the big improvements in HVDC technology. Today, HVDC technology is used as a highly efficient alternate for a huge amount of electric power transmission. Installation cost of HVDC transmission system is more than that of HVAC transmission system. Naturally, only AC power voltage can be stepped up or stepped down using power transformers. Hence, for HVDC transmission, we have normal HVAC power transformers at both the ends. Then there is a converter station at sending end of line, which converts stepped up AC power into DC power. This DC power is transmitted over the distance by DC transmission lines. At the receiving end, there is an inverter station which converts DC power into AC power, which again can be stepped up or stepped down as per the requirement using power transformers. These converters and inverter station increase the capital cost of HVDC power system as compared to the capital cost of HVAC power system. As shown in the graph, up to the break-even point, that is around 600 kilometers, cost of HVDC transmission is higher than that of HVAC transmission, whereas after 600 kilometers, cost of HVAC transmission is higher than that of HVDC transmission. Hence, for transmission beyond 600 kilometers, HVDC transmission system is economical as compared to HVAC transmission system.